right. It's 11, so thanks for staying awake through the first hour of the tutorial. This will be the second, where we will make use of the bound that we have derived from the first hour in order to explain one notion of optimality of evaluating these queries. I'm going to tell you about three classes of algorithms. I am going to name them JAT, VAT, and YAT. I think this is the first time that they occur in the literature, so I'm very proud of these acronyms. So this is one reason I didn't want to give Wolfgang the slides beforehand, because some elements of surprise is more interesting. Okay, so let's go talking about worst case optimal join. So I mentioned this before. So we've fixed a query, and for now, let's just say it's a full conjunctive query. And we have a statistical profile, which is basically just a set of degree constraints, and we want to compute the output. And one notion of worst case of optimality is that if the runtime of the algorithm is the input size plus the worst case output size, then that could be one way you might be defining a notion of optimality. And in database literature, we typically hide some polylog factors and also some factors that depend on the size of the query. And because the query is considered to be a lot smaller than the database, but this factor could be humongous in practice, and we really have to care about them. But for the purposes of this talk, I will kind of ignore factors that depend on the query size for now. Okay, so there will be a hierarchy of algorithms, which I will call them one join at a time, one variable at a time, and one inequality at a time. So that explains the acronyms. And the main theme of the talk will be that you can actually find the algorithm in the pudding. So the proof is in the pudding, and then if you look into the pudding, you'll find the proof, and from the proof, you'll get the algorithm out. Or pudding. All right, so we'll see how we can turn a proof of the into an algorithm, and this will be the central theme of the talk. All right, so remember that we had this hierarchy of bounds. I didn't describe some of the other bounds, but effectively what is going to happen is the following. We have algorithms that meet some of these bounds. So for example, if you go back to this quantity, we didn't really know how to compute this quantity, right? Because it's the entropic bound, approximation, and it's maybe too hard to compute. So what we'll do is we take an upper bound of this, an approximation of this. It'll be a little bit worse than this for some queries. And if the runtime matches the upper bound, then the runtime would be worst case optimal if that bound is tight under certain constraints. Okay? So when we have a hierarchy of bounds like this, you will see that, for example, for the integral edge cover bound, a JAT algorithm will achieve it. For the AGM bound or chain bound, a VAT algorithm, variable at a time, will achieve it. For the polymetroid bound, the only algorithm known is one inequality at a time algorithm. And these would be worst case optimal depending on what you assume about the query and what you assume about the constraints. So if the bound is tight, then that algorithm is worst case optimal. Okay? But we have a kind of a hierarchy of bounds and algorithms like this. Yeah? So in some sense, every algorithm is worst case optimal. Depends on what you assume about the query and about the input. Okay, so let's look at the JAT algorithm, and I'm going to spend just one slide on this. So in traditional databases, what happens is, suppose that you have a triangle query like this, RAB, SBC, TAC. A typical query plan will say that, well, I will have to look for a query plan in which I will join two relations at once. And Yuri asked about what a join means. It just means when we are joining, let's say, R and S, that means we are looking for all triples ABC for which AB is in R and BC is in S. So that's what a join. It's like a constraint satisfaction problem. And the traditional databases are built on this kind of binary join plan. So this is a query plan that says, why don't we join R and S first? We look at all the triples ABC for which AB is in R and BC is in S. And then we take the result of that, we join with S. Right? Or you could have this plan, you join S and T first, and then R, or join R and S first, and then T. Now it turns out that for this input, no matter which pair you join first, you will get an output of size quadratic. But this is obviously not worst case optimal because it is lower than what, higher than what the bound predicts, right? Is answer 1.5. So obviously a JAT algorithm is not going to be worst case optimal for this query. So this is the only slide I have on JAT algorithm. So let's look at the next class of algorithm, variable at a time. And here, so as a reminder, in the last lecture, we showed the following. Given this triangle query, the size of the output is bounded by basically R to the lambda R, S lambda S, and T to the lambda T, given that the lambda is a fractional edge cover for the triangle. So the sum of every pair of them is at least 1, and then the lambdas are non-negative. This came from the AGM bound, or fractional edge cover bound. And obviously, if you plug in an actual graph, you could get something like e to the 1.5. Let's see how we can prove this bound, but not using the entropic approach like before. We are going to give a different proof for this bound. And this new proof is going to be very naturally turned into an algorithm. It's extremely natural. Hopefully, I will convince you of that. So let's consider one section of this query. So this is triangle query, but I'm going to consider the section that corresponds to a particular value A in the domain of the variable A. So this is like a subquery where we specialize it to just one single value. And so now, if we want to list all of the triples ABC for which this section is true, right? So then what we need is basically all of the pairs B and C for which the little b is in R, which is the projection of R onto the part of R where A is little a. Right? And then BC itself has to be in S, right? And then C has to be in the projection of T onto the C column. Right? So that means that we need BC in this intersection. It has to be in S and intersecting with the cross product of the projection of R onto B and projection of S onto C. Right? It's in this intersection.
So the parentheses go like it should be parentheses around the product, right?
That's right. Yeah. Thanks. Yeah, so the parentheses should be around this cross product. So S is on BC dimension, and then this cross product is also on the BC dimension.
Okay, that should be E instead of S.
It should be. Oh, I'm sorry. Yeah, there should be T. It should be T. Okay, so S intersecting with R, projection of R cross product with projection of T, but with a fixed value of A. Okay, so here's a trivial observation that the number of such BCs, because it's in the intersection of two sets, it is going to be smaller than the smaller of the two sets. Right? The intersection of two sets is always bounded by the minimum of the two sets. And the minimum of the two sets is, there's a cross product, right? So you can multiply them like this, right? Now, the minimum of two quantities, of two non-negative quantities, is going to be bounded by the geometric mean. So I can put in lambda s here and 1 minus lambda s here. So the min is bounded by the geometric mean. And finally, because lambda s plus lambda r is more than 1, right? So now I can replace 1 minus lambda s by lambda r. And also lambda s plus lambda t is more than 1 because of the fractional edge cover. So this can be replaced by lambda t. So now we have, for this section, this is upper bounded by this, right? So this is just upper bounding one section of the query. Happy so far? So, okay. Now all we have to do to bound the actual query size is to sum over all possible a's, right? Because we are summing over one a at a time. So it's just summing over all possible a's. And now we are replacing this with the bound we just got from the previous slide. Right? And then we can factor out s to the lambda s. And we have this quantity. And now we apply Howder because lambda r plus lambda t is more than 1. So you can push the sum inside the product, but you get an upper bound. That's the Howder inequality. And now this is the sum over all of the a sections of r, so which is just r, and sum over a sections of t is just t. So that's how we get the fractional edge cover bound without using the entropy argument. Okay, so the beauty of this proof is that it actually turns into an algorithm extremely naturally, because all we did was, well, if you want to prove a bound like this, let's just iterate over all values of a, and then for every a, find BCs in this intersection. Right? So that's what the algorithm is. The algorithm is in the pudding. Is it pudding or pudding? Anyway, so what we do is we iterate over all a's in common between r and t, and then iterate over all b's, iterate over all c, condition on that a. Right? So it's like a conditional search algorithm or a backtracking search. Condition on a, look for the b. Condition on a and b, look for the c. So it's just backtracking search. And well, in English, all we are doing is for every a, let's basically enumerate all ABCs in this section of the query. Oh, I'm sorry. There should not be this vertical bars here. I'll fix the slide. This is just kind of the selection of the output, but on a equals to little a. Okay? And how long does this algorithm take? Well, it actually came almost identically from the proof of the upper bound. So the algorithm, we are iterating over little a's, right? And then we can compute the intersection of two sets in the time that is proportional to the smaller of the two sets, right? Because you can iterate over a smaller set and look up in a bigger set with a log factor loss. And so the search time is basically this much. But now I'm just repeating the proof that we just did for the upper bound. Because once you have the min, then you can replace it by geometric mean, and then apply Howder to get this quantity. And so the runtime is exactly as predicted by the bound. It came exactly from the proof of upper bound. Okay. Any questions so far? So that's just for the triangle, right? So now, what about in general? It's identical. The proof is virtually identical to the triangle case, except that we have now a fractional edge cover of the hypergraph of the query, right? And then the bound looks something like this: a product over r to the lambda, rs to the lambda s. There's one lambda for every edge in the hypergraph.
So can you just check something about the triangle algorithm? The algorithm does not depend on the values of lambda, right?
On the value of what?
Of the lambdas, lambda r, lambda t, lambda s. They do not intervene in the algorithm, and the algorithm is satisfies this bound for every lambda.
Exactly. Yeah, okay. Yeah, good question. So the question was, the algorithm, so as long as the lambdas form a fractional edge cover, and this is an upper bound on the runtime of the algorithm, which means that the algorithm runs in time minimum over this quantity over all fractional edge cover lambdas, which is the edge bound. Okay, so the general algorithm follows precisely the same script. We take the fractional edge cover, There's one lambda for every relation in the input. And then you can condition on one variable, on value of one variable, right? So then you are partitioning the query into two parts. The parts that depend on the variable, which is here, and the parts that does not depend on the variable. So that's that section. And we can basically, by induction, we sum over. So this is a proof of the inequality. So we just sum over these sections, right? So the sum is broken up into two, a product of two things that not depend on A, then the things that depend on A, and then applying Holder, we will get exactly this bound. It's precisely the same proof. And then the algorithm is also the same. It's just say that, well, why don't we iterate over all of the values in of the relations that contain this variable A, and for each one of them, recursively compute the little section on the variables that are not A, right? And then we just report that section along with the value A, and then the runtime follows precisely from the proof. Okay, so that's basically the VAT algorithm, one variable at a time algorithm. Okay, now the AGM bound as is actually does not apply for degree constraints that are beyond cardinality constraints. However, we can generalize this algorithm a little bit to the chain bound, which is basically a bound that has a variable ordering that I skipped over from the previous lecture. So I'm not going to have time to go through this, but I just wanted to point out that this algorithm actually applies to an arbitrary query under one extra assumption, which is that you have to supply it with a variable ordering to, you condition on by A first and then B and then C and so on. And this variable ordering has a humongous effect on the runtime of the algorithm. And the problem of deciding which variable ordering to choose from is NP-hard. And that's one of the main tasks of the query optimizer, to choose the right variable ordering. Go ahead, Nat.
The choice of the variable ordering does not affect the worst case optimality of the algorithm. So for any variable order, your algorithm would be worst case optimal. It's just that in practice, there may be huge differences between the variable orders.
Yeah, so Dan's question was the effect of, or comment was the effect of variable ordering on the worst case optimality of the algorithm. And yes, it's correct that for cardinality constraints only, then the variable ordering does not have any effect on the worst case optimality. However, if we go beyond cardinality constraints, then the variable ordering also has an effect on the worst case optimality. Because, yeah. So you, for some constraints, if you follow one particular order, you might activate that constraint. But if you select a different variable order, constraint may not be activated. And that has an effect on the worst case output size now. Okay, so now let's come to let's have a little detour of before describing. Go ahead.
What would go wrong if I had projections in the query? What breaks down here?
Yes, so the question is, what if we have a projection on the query? So there are two things that will break down. One is the worst case size bound on the output will break, because if the query is a Boolean query, then the output size is just 1, and our notion of worst case optimality doesn't quite apply. So in the third lecture, in the third tutorial, I'll come to that. So for now, let's just stick to 4 conjunctive queries. Okay, so before describing this probably most interesting class of algorithms yet, we have to talk about Shannon flow inequalities. go ahead. All right, so a little reminder that so we describe an algorithm to achieve the AGM bound. We say that it can also achieve the chain bound. But now let's talk about the polymatroid bound and see if we can actually achieve a runtime as predicted by this, which can be a lot better than the other two bounds. Remember that our goal is still here, right? But we have no idea how to do this in general, so we kind of had to relax things all the way up to here, and let's try to achieve this bound first. Okay, so this was a theorem that I quoted earlier, that the bound of the output size is bounded by the maximum over all polymatroids that satisfy the degree constraints. And the degree constraints of this form. So h of y given x is less than or equal to log n. Right? So the degree constraints are now converted into a constraint, a linear constraint on this space of vectors or space of functions. Okay? As a vector space, this has an exponential number of components. Right, so let's write it down more explicitly. What do we mean by polymatroid? What do we mean by degree constraints? Okay? So the problem is we want to maximize h of v. V is a set of all variables subject to the degree constraint. So h of y minus h of x is less than or equal to log n. So here I'm assuming that y is a superset of x, just to remove the annoying y union x every time. This is without loss of generality. So this is a degree constraint. And then we have to write down the other three constraints that are from the polymatroid constraints. So the first one is submodularity. All this is saying is, h of, if you condition on more, then you will get the conditional entropy to be reduced. So that's what I'm saying. Like if you know more, then the degree of uncertainty will become less. So that's what submodularity means. So that's this constraint. And then the next one is that is monotonicity. It says that h of x is less than h of y if x is a subset of y. So obviously the degree of uncertainty when you have more variables is going to be more than the degree of uncertainty when you have less variables. So that's what this means. And then entropy is non-negative. Of course, I'm talking about entropy, but these are only polymatroids. But the inspiration of where these inequalities come from, these are called Shannon inequalities. They all come from the information interpretation of these quantities. Okay, so now the first thing we want to do is actually create a dual variable for every of these linear constraints. So there's one delta for every degree constraint. There's one for every submodularity constraint. And this is over all pairs ij, for which I is not a subset of j and j is not a subset of I. So there's a lot of these guys. Right? It's quadratic, exponentially quadratic, or quadratically exponential. And then there's a monotonicity constraint. It has a mu dual variable. So there are three sets of dual variables, delta, sigma, and mu. And now, when we write down the dual of this linear program, so one way to solve this linear program is just to solve the dual. Right? It will have the following form. So this will be min over the dot product between the delta and the log of the degrees. Right? This is very much like in the fractional edge cover bound, right? You take the dual, it's precisely the same quantity in the fractional edge cover bound, except that the constraints are more complicated. Because in the fractional edge cover bound, you just have fractional edge covers constraint. But here, there's one constraint for every subset of variables, and I will not bother you with going through the details. It's just basically there's one constraint for every subset of variables. And it measures a certain excess of flows going to that subset of variables. And here's a picture of how to measure excess. So if you have, for example, a subset of variable z, then all of the sigmas for which z is at the bottom of the sigma of this diamond is going to contribute positively to the excess of z. Right? And there's also a negative contribution. So if you would like to kind of have a pictorial little illustration of how these excesses come about, then we just look at this picture. I wouldn't expect you to kind of get the details of this. I just want to get a theorem statement out of the dual formulation. Okay, so now that we have the dual variables, now we are ready to define something called the Shannon flow inequalities. So given the deltas, these are basically the dual variables corresponding to the degree constraints, right? Given the non-negative deltas. Then if the following quantity holds for every polymatroid, so if h of v is less than delta y given x times the conditional entropy or conditional polymatroid h of y given x. If this inequality holds for every polymatroid, then it is called the Shannon flow inequality, which is by definition. So for some deltas, this inequality will not hold for every polymatroid. For some other deltas, it will hold for every polymatroid. And for those, we are going to call them the Shannon flow inequalities. So it is known, the following is known, that delta defines a Shannon flow inequality if and only if you can extend it to dual feasible. This is the reason why I had to define the dual LP just now. So this is kind of a equivalent characterization of the deltas. So you can.
I got lost. What is this P?
What is
H of P?
V is a set of all variables.
Oh, okay.
V is just a set of all variables. Thanks. So the question was, what is this V? Because we are maximizing, the entropy of all variables in the Y for the upper bound. Okay, so that's one way to characterize deltas. So it's related to the dual LP. Now, so here's one thing that you might be able to relate to, that if the degree constraints are all cardinality constraints, that means the X part is all empty, then these are precisely the Shearer's lemma. So for those of you who are familiar with Shearer's lemma, it's basically an inequality of this form where it's, the coefficient on the right-hand side will have to form a fractional H cover. And that holds for all polymatroids. So this is a generalization of Shearer's lemma into general degree constraints. So it's not just cardinality constraints, but the X part can be non-empty also. Okay, so that's a. Go ahead.
Shearer's lemma, on one side we have entropies over the variables of one relation. But here I see h of y minus h of x. So how can I recover the h of xy, let's say?
Right. So the question was, in Shearer's lemma, we only have, like delta times h of y. There's no x in it, right? But if x was empty, then h of x is 0. So that's how you get Shearer's lemma. Okay, so as soon as you see an example, things will hopefully make more sense. So the first example of a Shannon flow inequality is a triangle example again. But in this case, we express it in the following way. So h of ABC is less than half of HAB plus HBC plus HAC. And this inequality holds for every polymatroid in 3 dimensions. Yeah? And we can give a proof of this, actually. Very simple. So this proof, I think probably a lot of people have come up with this proof like on their own. But the first time I learned about this proof style was from a really interesting paper, Radhakrishnan, 2003, Entropy and Counting. And it goes something like this. So we start from the right-hand side, and then we do the following. So h of AB, but you can write it in a telescoping way, right? You h of A plus h of AB minus HA. So that means that this is just a conditional entropy of B given A, right? So this is a decomposition of h of AB into two terms. Yeah. And then we apply submodularity. So here h of BC mapped down, h of BIM moved it over here, AC moved it over here. So the only thing that I applied was h of A is more than h of A condition on BC. Right? Because when you condition on more, the entropy will reduce, the degree of uncertainty will be reduced. So that's submodularity. But now you can group these two together. This is a composition step. So now h of A given BC plus h of BC, just like this guy here, right here, is h of A BC. Now we have one term on the right. So far we got one h of ABC on the left-hand side. Yeah. And now let's look at this term. We apply submodularity again. So now we condition on both A and C, so entropy will be reduced. And apply composition again, we get a second term on the left-hand side. So now we have just proved the inequality. This goes to this. So basically, in these tutorials, you see like different ways to prove the same thing. And then each one of those ways turns out to give you kind of an algorithmic idea in some sense. Okay, so that's for the triangle query. Now, I'm not going through this in detail, but you can verify at home that this is no longer a Shearer lemma type of thing, right? This inequality actually holds for all polymatroids on 4 variables. This was from Dan, actually. Dan came up with great examples, as always. And you can kind of trace through the steps of this algorithm, and you can see that starting from this right-hand side, you just do decomposition, submodularity, composition, and so on. There are only three things that you can do. It's like an inference rule. You just keep applying these inference rules, and eventually you end up with one side of the inequality from the other side. It's not obvious that this always exists. Right? However, for the 2 examples that we have seen, actually, these steps exist. Go ahead now.
Is it possible in general to have a way to explore the space of possible steps you apply there to try to prove whether an inequality exists or not? Is there something like that in this case? I guess this is the open question you mentioned. Perhaps.
Right. So I think there are 2 ways to phrase your question. So one is, how do we kind of come up with a proof of an inequality, given that we didn't know it beforehand whether or not the inequality is valid, right? And I think Raymond Young and others have worked a lot on like a software system to go discover inequalities at how, not only for polymatroids, but also for like entropic functions. Now, in general, given an inequality like this, you could use the previous thing that I mentioned to verify it, because delta defines an inequality if and only if there exists sigma and mu, so that this is dual feasible. So you could go about solving a linear program to decide validity of inequality. However, there's a very, very subtle difference. Here, we are talking about kind of a linearization of the steps. Now, typically, when you take a linear program, you have to take a linear combination of dual constraints to come up with the inequality. But this is a very specific, like, linearization of these, the linear combination, and they are not the same. So in general, searching for this is sort of like the chase in database, because you have the inference rule, right? So you kind of chase these rules, but you may end up with something, maybe even higher than what you want to prove. So I think it's an interesting and good question in general on how to apply these 3 rules, like repeatedly in some ways, to come up with a proof. It's not obvious.
Maybe I didn't quite understand the question is, but so like, so there may be valid inequalities that are not provable via decomposition, submodularity, and composition?
Well, we have a theorem that shows that you can always come up with that,
Okay.
but it's not an obvious result.
So, so the difficulty is that if you, so the test inequality is a sum of some modularity and monotonicity inequality. It's easy. So you can find that sum using the dual. The problem is that if you compute the partial sums, you might get negative terms. And if you want to think about an algorithm, negative terms mean nothing to you. So you don't want negative terms, you only want positive terms. And that is not obvious that you can always get it.
There were two other, Remy?
Yeah, this is follow up to that question. So one helpful keyword might be automated theorem proving. So that's a whole field. I don't know if we have experts here. Starting with how, if you give me a bunch of the axioms, and I automate my proof about.
Yeah, great comment. Yeah, so the chase is probably a special case of automatic theorem proving.
Yeah, I want to ask, you said there was a software that does this or does something like that?
Yes, so there was software that kind of tries to come up with a verification of the validity of entropic inequalities.
Okay, so you give an equality, then it will automatically verify if it's correct or not.
Yes.
What's the name of the software?
I will send a link to you.
Okay, thanks.
Okay, so now in general, so let's just summarize. So we can show the following. So what we are interested in is the polymetric bound, right? And by taking the dual, you can write it as a dot product of the delta and log of degrees. And from this delta, we know that this inequality is a Shannon flow inequality. That means that it holds for all polymetroids. So this is all we know so far. And it turns out that you can prove that given a Shannon flow inequality, we can come up with a proof sequence, just like in the two examples that we have just shown. One step at a time, you can do the decomposition. Well, yeah, this will be a composition, right? You compose two terms into one. You can do a decomposition. You decompose h of y into h of x plus h of y given x. You can do submodularity. And then there's, I didn't show this in the examples, but you can also use the monotonicity to replace a bigger term by a smaller term. And in this sequence, you will go from a bigger sum to a smaller sum, and eventually you get to the left-hand side of the inequality. So that's a proof sequence. And there was a lemma from our paper in 2007 with Mahmoud and Dan that shows that there is a proof sequence for every Shannon flow inequality. Now, if you are looking for open problem, this is a great open problem. So the length of this proof sequence is terrible. And I don't even remember the formula, maybe Mahmoud remembers. But it is very, very big. And we don't know how long the proof sequence is. Okay? But why does this have anything to do with join algorithms, right? So now let's go, proof is in the pudding. Let's go to join algorithms, which is the YAT algorithm. So the essence of the idea is the following. So given a proof sequence for the Shannon flow inequality, we'll come up with a join algorithm to compute the query. And it goes like this. So every step in the proof sequence will be turned into a relational operator, like a join or a projection or a partitioning. So if we have a composition of two things, then this will become a join operator. If we have a decomposition, then this will become partitioning the data into parts. If we have a move from a bigger term using monotonicity from h of y down to h of x, this will become the projection. And if it's submodularity, then just it's just a rearrangement of things. So using this conversion, we proved basically, came up with an algorithm. This is called Panda, that shows any conjunctive query in time that is predicted by the polymatroid bar. Okay, so let's look at 2 examples. And I will have just enough time to go through these 2 examples. One of them is just a triangle query. So it should be very easy. And you probably have seen this algorithm before. Okay, so it goes like this. So we have a triangle query, R, S, and T. Let me define this first beforehand. So R heavy is the part of R for which the degree of A is more than square root of n. And R light is the part of R for which the degree of A is less than root n. Okay. Let's just partition the R into 2 parts. The part that contains the heavy hitters, and by heavy I mean the ones whose degree is more than root n, and the light hitters, the ones that are less than root n. Okay. So it's just a partition of R into 2 parts. This may be a little bit magic at this point, but I'll explain how we came up with this to begin with. Okay? But for now, let's just say we have this partition. Someone gave us the idea.
One of them is light.
Yeah.
Oh yes, thank you. Yeah, this is the light part. So the heavy part is the one that is greater than root n, and the light part is less than root n. Okay, so now I'm going to use the proof sequence and to turn it into a join algorithm, a way to compute the output. But the way to do that is the following. So for every term on the right-hand side of the Shannon flow inequality, we will associate it with it a copy of one of the input relations. So H, AB corresponds to RAB, HAC is SBC, HBC is SBC, and then HAC is TAC. I'm sorry about the wrong ordering. But now let's focus on this term first, because in the proof sequence, we apply the decomposition step to this term first. Yeah. So we decompose this into H of A plus H of B given A. Now what does this correspond to? Well, this will correspond to essentially decomposing R into 2 parts, the heavy part and the light part. Okay. So I'm just chasing the colors now. Now let's look at the next step. The next step was submodularity. So, A was replaced by a condition on BC. So this corresponds to doing nothing except for a little bit of rearrangement where we are about to compose these 2 terms together. So that will correspond to joining the heavy, R heavy, and S BC. It corresponds precisely in a one-to-one manner from the proof sequence to the join operator. Okay, so in the inequality, we compose those 2 into this join, right? And in the database, we are going to join R heavy with SBC into an intermediate result. I'm going to call this I heavy of ABC. Again, the join means, I'm going to compute a table, ABC, for which AB is in R heavy and BC is in S. Yeah, that's just a join operator. And the next step is submodularity, corresponds to nothing, just some rearrangement. And then finally, when we're about to compose these 2 to get H of ABC, then here we get the intermediate results corresponding to the light branch of the query plan. So I've just described to you kind of how the correspondence between the inequalities, the proof, and the association between every term and some relation on the right-hand side.
I'm not sure I understand the query plan because the heavy hitters, you didn't join them with T at any point?
Great question. So I will explain why this is correct because of next time.
So I'm confused. You said the proof sequence can be doubly exponentially long, but the algorithm runs in polymatroid context. So what's it?
Yeah, so the question was the proof sequence can be very, very long, doubly exponential, and the algorithm is, well, that's when this big O of theory is hiding all of the factors that are dependent on the query. Yeah. So anything that's dependent on the query size is kind of, is under the rug. Okay, so I'm going to answer your question. Why is this even correct, right? So here's another proof that this is correct. Now I'm going to give you a precise query plan that corresponds to this type. And it goes like this. So the real query plan is when you do a decomposition, right? You basically turn this term into a union of two things, right? Yeah. This is kind of like a it's just a data partitioning, right? Now, once you turn this term into a union of two things, and you can distribute the OR over the end, and now we have two terms, right? The heavy is on one side, and the light is on the other side. Yeah. And then the next thing that we were going to do, according to the proof sequence, is you join the heavy with S. So now you have the I heavy on one side. So we haven't lost anything yet. And then on the other side, we have the light part of the query. And in the end, obviously, once you have to compute this, you will have to kind of, on the heavy side, you have to filter the result with T. You have to do the join again. But the last join is trivial because once you have a relation that spans all variables, then we just scan over it and filter down the result. So that's the query plan. That's the actual query plan. And the beauty of this is that you can show that the size of the heavy side is less than n to the 3/2, and similarly for size of the light side, also less than n to the 3/2. And that's precisely because of the way we defined heavy and light, right? So for heavy, for example, it was all of the ABs for which a degree was more than root n. So the number of A's whose degree is more than root n has to be less than root n. Because you cannot have too many heavy A's, right? Otherwise, it would be more than the size of R. And so because the number of A's, heavy A's is less than root n, so when you join these two together, you will get something smaller than n to 1.5. Similarly, for the light part is easier. So here, the degree of A is less than root n. So for every A, you have at most root n B's, and then you multiply that with the size of S, which is n. Or is it the other way around? I should probably define the degree with respect to B, but I think you get the idea. Yeah. So, oh no, it's fine. This is joined with T. So, yeah, for every A, there are at most root n B, right? And then we are going over n things in AC. Right? So for every AC tuple, the number of B's is root n, and so the light part is at most n to the 3. Okay, so that's the essence of the one inequality at a time algorithm.
Is there a general way to tell which is the threshold?
Awesome. So my next example is about how to tell what this threshold is, because in general, R could be very different from n, right? And S could be like really big, or it's very small. T is it's arbitrary. So how do we even tell what the threshold is? The root n was a very convenient way of deciding the threshold. But in a database with arbitrary degree constraints, the threshold can be very wildly different. So the next example is meant to illustrate that. So this comes from the following query. We have a path of length 3, so A, B, B, C, C, D. And then let's say we have the silly hash function that for every AC, I get a D, right? Some kind of hash function. And from every BD, I get an A. So we don't know. The reason I push hash here is so that you cannot do the reverse lookup from D to recover AC. Okay, so this query, that's actually the corresponding Shannon flow inequality. I didn't show you the proof steps of this Shannon flow inequality because it's a bit too long. But from this, what you can do is the following. You know that HAB is smaller than log R, right? So you can plug it in. H of BC, log S, H of CD, log T. Now, the hash function means that the entropy of D given AC is 0 because it's a functional dependency. So you can put in 0 here and 0 here. So you know that the query size is bounded by square root of IS and T, okay, from this Shannon flow inequality. So now let's try to come up with a algorithm that will answer this query in this time. This is becoming a little less trivial. You cannot do the one variable at a time algorithm anymore. So we just chase through these steps. Now, again, I'm not going through these steps in any detail, but to answer Albert's question earlier, the algorithm will go kind of like this, right? Just chasing through the query plan, just like before. But the main question is, how do we even define this heavy and light so that the runtime is as predicted by the linear program? Right? So let's say that I solved the linear program and I have this optimal solution H star, let's say. So what we can do is the heavy part of S is going to be defined by exactly the quantities that came out of this entropy, this optimal linear program. So it came out of the the solution to the polyimage fiber. Okay? So this is the heavy part. This is the light part. It's just the threshold is defined that way. And it turns out that if that's the case, and you can kind of chase through the proof, and you show that the size of the intermediate relations, S light joined with T, or S heavy joined with R, they are going to be bounded by, in this case, H star of BCD, and this is H star of ABC. Under some assumption. So you have to start with the primal optimal solution and the dual optimal solution. And because of that, due to complementary slackness, you will get this equality out. Yeah, so the analysis is kind of easy, but it's not, you really have to delve into the details of the linear program to know for sure that you get an equality here, and the runtime of the bound of all of the intermediate results are really upper bounded by the polyimage fiber. Okay, so I will upload the slides, and you can kind of chase through the details to get it. Okay, so that's kind of two illustrations of how Panda work. Now, in Panda, in reality, it's much uglier than this, unfortunately, because of the following. I'm not going to read through the slides because of the following. So when you come up with a query plan like this, you have to make sure that every time you partition something into heavy and light, they will end up in like distinct branches of the query plan. Right? You cannot like recombine like a heavy and a light part of the same thing back together. You essentially have to show that in every branch, so every time you do a partitioning, you basically partition the thing into two parts, right? And then you partition again, you will get two parts from here and two parts from here. You have to make sure that in the end, every term will end up with the output. It's a little bit hard to describe, but you can see from this that it's not obvious that every proof sequence is going to end up with a correct result, right? Because what if you get stuck somewhere in the middle? Yeah? So that's basically the intrinsic difficulty of realizing this idea in general. So we had to kind of make a compromise where instead of just a heavy light partitioning, we partition the relation into a logarithmic number of subrelations, and the thing has a polylog factor is very very big. Okay, but I hope you get kind of the gist of this idea. Go ahead.
I have is, so here we show that we partition into relations, right? So my recollection is that in Panda you also have perhaps to partition on intermediate relations, right? So you also get for those relations, intermediate relations, what is the actual threshold? You can get this, you read it out from the optimization solution, right?
Yes. So yeah. So in Panda we have like a partitioning of this light into I light heavy, and so on, right? But the same proof strategy will still flow through. You can think of it as a kind of an induction, right? If your proof works for this term, and your proof works for this term, then together they will work for the original query. So you can kind of induct on the query plan and repeatedly apply it.
So can you say anything about the case where you only restrict yourself to partition and input relations? So what would happen in that case? Because this actually seems to be a simpler approach. I guess you of course will not get the bound you want, but you know anything about which queries could still be done like that, it would be, let's say,
Yeah, so we know of a few classes of queries for which the decomposition step in the proof only happens at the beginning, such as the AGM bound, for example. And you only have to do decomposition of the input relations. You don't have to decompose an intermediate relation. But in general, I think it's still open, like characterized precisely for which degree constraints you can only do this in the beginning, and you don't have to decompose an intermediate result like this.
Just to add to this, if I remember correctly, Marx's original algorithm that did some had like did not at least a modular, but some modular O of the some modular width did that partitioning, but then I think they couldn't get to the exact type bound, right? Because here we want to achieve the exact bound, so there they were off some constants. So
yep. So here are some open problems along that direction. So as I mentioned earlier, the proof sequence length is still kind of terrible. And then, in the actual algorithm, we have some steps that are not as clean as I would have you believe. And there's a humongous polylog factor. It could be, you can argue that maybe there could be a more natural algorithm than Panda. And then there's a conditional independence constraint that may actually break Panda too. And this can bring the bound even down below the polymetric bound. So these are some of the few open problems that we have. So hopefully I gave you kind of enough of an overview of 3 classes of algorithms and 1 algorithm that meets the polymetric bound. And in the next next tutorial, I'll talk about queries with projection. So far we have only done 4 conjunctive queries, and projections open up a new kind of world. It's a really interesting area. Well, see you at 2 p.m. Yeah.
We do have time for questions. Yes.
So, if I understood it correctly, these approaches still have a high complexity on the number of variables in your query, right? Is this not an issue in practice?
It is an issue in practice. Yeah, anything that is more than quadratic is a big issue in practice.
But even on the number of
Even on the number of variables.
Yeah, so for this bound, actually, this lower bound that we want to establish for the length of the sequence, right? What kind of techniques do you have in mind, actually? What kind of techniques can be used for that? Like, I'm thinking about proof complexity or something like that, but is this related with that, or?
Yeah, I would have to rely on Albert or someone who's more, proof complexity expert.
Yeah, but is there anything known about this Shannon inequality, something that can be used, actually, in terms of the length of the sequence or something like that?
Yeah, I don't know of any.
I actually had a simple question. I asked the expert, so you have a Shannon inequality, and all the coefficients are integers. Okay, very simple. So now this, this is a sum of some modular inequalities, which are integer coefficients as well. Do you need to have a linear? Do you need to express this linear inequality with which coefficients are integers as an integer combination of some modular and monotone inequalities? And for all examples we know, that's the case. You only need integer coefficients. That usually gives you an upper bound on the length of the proof sequence because integer cannot grow. So you, but it turns out no. There is, I think Ilan Studeni or Laszlo Csirmash, one of them, I don't remember one, pointed me to a paper which is very, very dense, and that has an example of an inequality with 5 variables. Which is integer, but you need combinations of fractional submodularity inequalities to get that inequality. Which means that the length of the inequality goes beyond what you can reason about.
say that last minute, goes beyond what?
Beyond what you can reason about just the integers.
So you mentioned there's one open problem exploiting conditional independence. So, but in your formulas, your derivations, you always use this conditional, instead of some of them were conditional. So I imagine that some of them will just be zero, right? So isn't that how you would exploit conditional independence in your setting, or you need something else?
Yeah, I meant something else. So conditional independence is basically if you look at the query and you take a separator, a set of variables that will partition a query into disconnected components, right? So you know that if you condition on the separator, then the components are independent from one another. And you can write that down as an equality constraint in the linear program. That equality constraint is different from the degree constraints that we have seen. And if you add that into into the set DC, it's no longer just h of y minus h of x less than n, right? It's actually there are more constraints, and that will reduce this bound down. But then we don't know of a corresponding algorithm to meet that new bound.
Does the generalization of the simplicity of queries using tree width, would that help?
That will be the subject of my next tutorial. Yes. So I'll come back to tree width and things like that.
Does the particular proof sequence, like I imagine there's a bunch of ways to get from A to B here, does that affect either meeting the bound or like practical?
Yes, definitely. Yeah. So if we can come up with an optimal proof sequence, then the runtime will be much better than a bad proof sequence. You can join things into an intermediate result that is too bigger than the bound.
So if you give up the requirement that you want to have like an upper bound always, but just some approximation of something, can you do something more or easier? I don't know how to phrase it, but.
I think our polymetric bound is already an upper bound on the worst case size. So in some sense, we are realizing that, or the chain bound, for example, then you have to go through a VAT algorithm.
Do you know if these rules are not redundant? And do you need them all?
You mean these steps or these steps?
I mean, this step. No.
Yeah, I think in the algorithm we need all of these steps. Yeah, we need all of these steps in the algorithm.
So you have examples where you need. And you know what I mean? Will it be that one can be expressed in terms of the other?
Oh, I see. Oh, I guess you are thinking about the proof complexity angle. I believe that we need to know. You cannot
believe.
Yeah.
I'm not aware of any formal that they are
algorithm or a variant of this algorithm, right?
Yes, so implemented in a sense that you can easily do query rewriting by hand because you can kind of take a query plan that you come up with using proving these inequalities, and you can write, SQL query or rel query following exactly these steps. And if you have the right threshold, then it can be pretty good actually.
Okay, thanks.
Yeah, especially for cyclic queries, like click queries or triangle queries.
So all we need is a compiler that translates the proof sequence into
Exactly, yeah. But I suppose that you need a partition operator that is very well implemented, and if the data size is too large, the issue of gathering data from multiple servers, you have to run into a lot of system issues to realize this.
But originally you said optimization means you do not know the query beforehand. But now you actually said, okay, but if we have this query, we have this proof, and then we can translate. But I mean, the general problem is.
Yeah, so in the optimizer, we would implement a proof sequence discoverer for an arbitrary query. Yeah.
But we would.
Well, so we have an algorithm to do that, right? Yeah.
Okay, if there are no more questions, then let's thank the speaker.